Hello everyone. Today, I am here to present my final project for the Neural Networks course, Heart Disease Prediction Using Multi-Layer Perceptron, MLP. Let me start with why I chose this topic. According to the World Health Organization, cardiovascular diseases are the #1 cause of death globally. Early diagnosis is crucial but often complex. My goal in this project is to answer a critical question. Can we use artificial intelligence to assist doctors in diagnosing heart disease using standard clinical data? To answer this, I built a binary classification model using deep learning. Let's examine the dataset. I utilized the UCI heart disease dataset, which is a standard benchmark in machine learning. It consists of 270 patient records and 13 features. These features are not just random numbers, they are vital clinical indicators: age and sex, basic demographics. CP, chest pain type, different types of pain indicate different risks. Cholesterol and blood pressure, standard health metrics. EKG results, electrical activity of the heart. A very positive aspect of this dataset is that it contains no missing values, as you can see in my analysis. The target variable is presence, 1, or absence, 0, of heart disease. The classes are fairly balanced, which is great for training. Before feeding this data into the neural network, pre-processing is mandatory. Raw medical data comes in different scales. For example, age is around 60, but cholesterol can be 300. If we feed this directly, the gradient descent algorithm will struggle to find the global minimum. Therefore, I applied standard scalar. This transforms the data so that it has a mean of 0 and a standard deviation of 1. Then, I split the data, 80% for training and 20% for testing. This separation is vital to evaluate how well the model generalizes to unseen patients. Now, let's discuss the core of the project, the MLP architecture. I designed a fully connected network using Keras. Input layer matches the 13 features. Hidden layers. I used 2 hidden layers with 32 and 16 neurons. Why these numbers? They provide enough capacity to learn nonlinear patterns without making the model too complex. Activation function. I chose ReLU, rectified linear unit, for hidden layers because it prevents the vanishing gradient problem and speeds up training. Regularization. I implemented dropout, 20%. This randomly turns off neurons during training, forcing the network to learn robust features and preventing overfitting. Output layer. A single neuron with the sigmoid function, which outputs a probability between 0 and 1. I compiled the model using the Atom Optimizer, which is widely used for its adaptive learning rate capabilities, and binary cross-entropy as the loss function. Looking at the training graphs for 100 epochs, the loss graph shows a steady decrease, which means the network is learning. The accuracy graph shows we reached a stability point. There is a slight gap between training, blue, and validation, orange, lines after epoch 20. This indicates mild overfitting, but since the validation accuracy remains high around 85%, the model is still reliable. Quantitative results are the most important part of a medical AI project. We achieved an overall accuracy of 85%. However, in medicine, accuracy isn't enough. We must look at the confusion matrix. Analyzing the quantitative results, the model achieved a strong recall rate by correctly classifying 16 of the 21 positive cases. This corresponds to a lower false negative rate of just 5 patients. Furthermore, the model generated only 2 false positives out of 33 healthy individuals. Minimizing these false alarms is vital in healthcare to prevent unnecessary stress for healthy patients. In conclusion, this project proves that artificial intelligence is not just about code and numbers. It is a powerful tool that can assist doctors and potentially save lives through early diagnosis. Thank you for your time and attention.